In this video, we're going to continue our coverage of Chapter 9. In the first video, we talked about network topology and a few related topics from the very beginning of the chapter. In this video, we're going to move on to the issue of addressing and forwarding and routing. If you haven't watched the previous video or read that material, you should do one or both before watching this one. Okay, so we're going to pick up at slide 9, I believe it is. Yes, addressing and forwarding. So when a network is big, it needs to be segmented into smaller networks, and those smaller networks are going to be interconnected in some sort of store and forward system. So for example, in the first set of slides, we looked at a very generic network diagram like this, where the white boxes represented end nodes and the gray boxes represented nodes that would store and forward messages or packages or whatever they were from one node to another. So for example, in this diagram we could think of, let me do a different, here we go. We could think of this as one part of the network. We could think of this as another part of the network, and we could think of this as yet a third part of the network. Okay, and these boxes here are interconnection points between the networks. Okay, and when we talked about this in the first video, we talked about how if these nodes were houses and we were shipping packages from one to another, this might be, say, something at the Albuquerque airport for FedEx packages. This might be the Memphis office, the national hub, and these might be hubs in other states. Okay, so the point here is that in a large network that is segmented, as that one was, okay, we're going to have some set of interconnection nodes. Okay, and we're going to basically be breaking up the network into a series of pieces that are each of which is interconnected via one of those nodes. Obviously, the larger the network, the more the levels of interconnection. So for example, if we're talking about, say, the internet as a whole, we could imagine probably dozens of levels of interconnection with various size nodes connecting those. Okay, so let's take the internet for example. So I'm sitting at my desktop computer here in Anderson School of Management at the University of New Mexico, and let's say I fire up Outlook here and I write an email message to a colleague, I don't know where, say at North Carolina, University of North Carolina, and I hit the send button. Okay. That message, let's assume for the moment it's one message as far as the network is concerned. How's it going to get from here to there? Well, the email analogy here is quite appropriate because like a regular snail mail or U.S. Postal Service mail or really any other kind of mail, that message is somehow going to have to be tagged or addressed. Okay, so if you think of, post office, old-fashioned, you stick a letter in an envelope and you put a stamp on the envelope. Well, what else goes on the front of the envelope? Well, there's two things that go on the front of the envelope. One is the address of where it's going. Okay, so you've got a street address, 1234 Main Street, Charlotte, North Carolina, and some zip code, and typically you've also got the name of a recipient at that address, since there might be multiple people at that address. Up in the upper left-hand corner, just in case something goes awry, you've also got the sender address, my address in this case. Okay, so that it can be, so that A, we know where the message came from, and B, if for some reason we fail to send the message, we know where to send it back to. Okay, so this idea of putting a message in an envelope and having the envelope have both sender and recipient address of some form is not unique to computer networks. It's been around as long as anything that we would call a post office has been around. Okay, so a central node, be it a router in a computer network or be it a local or regional post office, has to look at all those messages or letters coming through, has to examine the recipient address, and has to forward that message on toward its destination. In some cases, that may be directly to the recipient's address, but more often than not, it's going to be to some intermediate node between that point and the ultimate destination address. So, for example, if I mail a message from my if I were to use snail mail to send a message from my office to that same person in North Carolina, it would, I'd put it in the outbox here. That would get picked up twice a day by UNM's postal service. It would go to a postal sorting facility inside UNM, which would take care of all the internal mail that doesn't require a stamp and send everything else off to the downtown post office. The downtown post office would look at that recipient address and say, hey, this thing's going to North Carolina. Clearly, I've got to get it to the other side of the country. Okay, and depending on that first digit or two of the zip code, it's going to figure out what plane it needs to put it on in order to get it closer to North Carolina. Okay, so it looked at that recipient address and forwarded the message, in this case, to a regional post office, say in North Carolina or somewhere in the southeast. That post office, once it received the message, would look at the recipient address, would forward it to the local post office nearest to the destination address. That post office would again look at the recipient address and say, well, this is going to 123 Main Street, and would assign it to a particular carrier route for delivery. Okay, so taking that analogy into a computer network, okay, when an incoming message is received by some central node in that computer network, we can basically break down the possibilities into two. Okay. And this first possibility you can simply summarize simply with the word local, okay? And this next one you can summarize with the word not local, okay? So, if the message were going to some other node on the same local network, so for example, if I was sending, I don't know, a pop-up message directly from my desktop to the desktop 2 offices down the hall, okay, that would go to the central node that connects both of our offices. That central node looks at the destination address, knows that where it's going is another directly connected node, and simply forwards it directly to that machine. End of the transport. So it only had to go through one central node. On a more general case where it might be much more distant, say me to an email server at Central UNM IT Services and from there to North Carolina, okay, it's probably going to go through several central nodes, and each of those would be generically called an interconnection point. Now let me just briefly digress into this issue of central node and interconnection point. I'm avoiding some very network-specific terms here. For example, router, switch, hub, wireless access point, okay, those are all things I'm avoiding, okay. Why am I avoiding them? Because for this discussion, it really doesn't matter what kind of device we're talking about that serves as that central node. There are, in fact, several different sorts of quote-unquote boxes that could serve as that switching or routing or forwarding facility. So I'm just kind of using the term central node, or if you like interconnection point, generically to refer to any device that could fill that role. Later on in the chapter, we'll get into discussing the distinctions among those various devices. Okay, so summarizing from here, once my outgoing message is received by the first central node up the line, okay, there is a basic decision to make. Is it local or is it not? If it is local, then it will simply be routed to the appropriate local node. If it's not, then it's going to go to another interconnection point, another central node further up the line or closer to the ultimate destination. Okay. So let's take a look at the layout of a typical complex network here, and then we'll put some of these routing and addressing issues into action. Okay. Over on the right is a diagram out of the textbook, which purportedly shows a typical campus network. Okay, with a backbone network as shown here on the lower right, a series of zone networks, and I have 3 here, one of which is shown in detail and the other 2 of which aren't, and then inside the North Campus zone network, some additional detail for particular buildings in that zone. Okay. We can roughly divide the kinds of networks in here into 2 classes. Okay, although I've actually got 3 different ones named here. Okay, there are local area networks, which typically deal with either a single floor or a single building. Okay, typically have less than, say, 50 nodes. Okay, that are members of those. Okay, and then we have wide area networks. Okay, a wide area network, quite simplistically, is simply anything larger than a local area network. Okay. One particular example of a wide area network would be a backbone network, such as that shown in the lower right here, corner here of this diagram, although you could think of the entire internet as a backbone network or wide area network. You could think of a network connecting an entire city as a wide area network. Clearly, wide area networks can run from fairly small to really huge. Okay, so there's lots of different quote-unquote sizes of wide area networks and various names that could be applied to those. Local area network, however, is much more specific. It implies an interconnected set of nodes, typically a few dozen or more or less, connected by one central node. Okay, so when I've got hundreds or thousands or tens of thousands of nodes, as we do here, say on the UNM main campus, okay, clearly I need one LAN is not going to cover it. Okay, so I'm going to need lots of LANs, and then I'm going to need ways of interconnecting those LANs. Okay, what the diagram on the right shows here is actually a pretty close approximation of the way things are handled on UNM and in most large quote-unquote campus environments. And note the term campus in this sense does not necessarily imply university. It could be, you know, a corporate campus consisting of multiple buildings. This could even represent the internal network of, say, a large skyscraper. Okay, but the bottom line is anytime you've got many dozens, hundreds, thousands, tens of thousands of nodes, you're going to have this sort of tiered approach to the networks. Okay, so how does a message move around? Okay, well, let's go on to the next. Let's go on to the next slide and go through a few more details before we do an example. Okay, so central nodes. What's the role of a central node? Well, first off, let's pick out the central nodes here. Okay, here's a central node. This is for a LAN. Here's a central node. Okay. Here's a central node. Here's one. These were all LAN central nodes. But then we also have zone central nodes in this case, which connect multiple LANs. Okay. And we have this campus central node. Okay. So essentially we have three levels of central nodes. Okay. These would be these three in Smith Hall and the one at Jones Hall would kind of be tier 1. So, well, maybe these would be bottom tier, whereas this campus central node would be top tier, and in this case we have a tier in between that we call zones. Okay. All right, so a central node, any of those three types, has to examine each packet address and determine, once again, is it local or is it not local? Okay. If it's local, the decision is fairly simple. Well, there is no decision really. I just send it to whatever the local node is directly and I'm done. If it's not local, then the question is, where does it go? Okay. Okay. Well, this question, where should a non-local message be sent, can be a fairly simple decision for some central nodes and a fairly complicated one for others. Okay. It is, in fact, quite a trivial decision if the central node we're talking about is connected to only one other central node. For example, these LAN central nodes here. Okay. Each of these LAN central nodes is connected to, what do I have drawn here, 12 end nodes and one zone central node. Okay. So looking back at this routing decision, if the address is local or directly connected, say this one, whoops, here, get my pencil back out, sorry. Say this one wants to send a message to this one, okay, then it's pretty straightforward. That message goes to here, the LAN central node looks at it, says, ah, that's another node on this network, and it simply forwards it right to there. We're done. Okay. If, whoops, wrong direction. If it's not local, then where to? Well, in the case of this particular LAN central node, that's also a pretty simple decision because there's only one other connection point for this node, and that's this one right here. Okay, so the local non-local decision, routing decision, or I should say the non-local routing decision, is extremely straightforward for most LAN central nodes, because in most cases the central node of a LAN is connected to one other central node upstream, and that's it. So anything that's not local to the LAN gets passed up to that central node. End of decision. Okay. All right, let's make it slightly more complicated, however. Okay. If the central node is connected to multiple other central nodes, okay, then we have a more complex routing decision. Okay. So for example, if this zone central node here in the campus back for the North Campus zone receives a message, okay, now it's got a much more complex decision. Why? Because it's not connected to one other central node, just this campus central node. It's also connected to 4 LAN central nodes. Well, we can rule out Smith Hall first floor's LAN central node because that's where the message came from. But maybe it's going to the second floor of Smith Hall, or maybe it's going to Jones Hall, or maybe it's going to some other part of campus, or maybe it's going to North Carolina. Okay. So these zone central nodes and the campus central node have more complicated forwarding and routing decisions to make because they have more complex interconnection to other central nodes. Okay. Whereas the LAN central node has a very simple decision to make. Okay, so how do we make these decisions? Okay, the basic concept here is what's called a forwarding table, and you can use the term routing table more or less interchangeably, at least for purposes of this discussion. Okay, what is a forwarding table or a routing table? Okay, quite simply, it's a list of addresses, and for each address or a group of addresses, okay, where do they go? Okay, the node to which those addresses should be sent. So you can certainly imagine, for example, this LAN central node having a forwarding table with 13 entries. Okay, why 13? Well, there's 12 end nodes here and 1 upstream central node. So it'll have the addresses of the 12 locally connected nodes. If the recipient address is any one of those, it'll simply send it down the appropriate line. If it's anything else, up it goes to the central node. You can imagine that this zone central node and the campus central node are going to have more complicated routing tables because they are connected to other central nodes and therefore have a larger number of ultimate destinations that they need to deal with. Okay, so the forwarding table of the LAN central node, as we said, is generally going to contain n plus 1 entries where there are n local nodes and 1 upstream central node. Okay. The forwarding table of an end node is even simpler. Okay. Packets to any address are simply going to be routed to the LAN central node. Okay, and I'll show you an example of that right here. Okay, here is the printout of the routing table, or a portion of the routing table for the computer on which I'm preparing this video. Okay, ignoring this interface list part, let's just look at this part that says IPv4 route table. Okay, you'll see there's 4 entries in here, but realistically there's only one that matters. Okay, note the network destination 0.0.0.0. Okay, what is that? That's shorthand for anywhere. Okay, a message to anywhere gets set to 64.106.58.1 via this address, which is my network interface card. Okay, so the bottom line is it doesn't matter what the outgoing address is. Okay, it's always going to get set to 64.106.58.1. Well, what is 64.106.58.1? Well, I'm sitting here in Anderson School of Management. Let's assume it's Smith Hall for the moment, on the 2nd floor of the West Wing. I'm in, say, that one right, that end node right there. Okay, and let's keep blinking with the wrong one. Where are all my messages going to go? Well, they're going to go to this central node right there. Okay, doesn't matter where my outgoing messages are. This is the first stop. Okay, so for an end node, the forwarding table is incredibly simple. It typically has 1 entry where everything is sent. For a LAN central node, the routing table or forwarding table typically has n plus 1. Okay, but as we get further up the line, Now the forwarding table gets much more complicated. Okay, so for example, this Zone Central node for North Campus Zone Network needs to know all the addresses covered by all the central node LAN or LAN central nodes within that network. Okay, within that North Campus zone, it's got to know them all. Okay. And so if something comes in from me going, say, to an office on a different floor in my building, it's got to know that there's a range of addresses controlled by a LAN central node that includes the address I'm sending it to, and it's got to forward it to that LAN central node. Everything else, by default, will get set up to the Campus Central node. Okay. Now note the Campus Central node here, and note I have a single arrow that says to the internet. Very often, for multiple reasons, one of which is simply redundancy and resiliency, this Campus Central node actually might have multiple connections to the internet. Okay, might have a dual, might have a fast one and a slow one, or might have a primary and a backup. It might have a dedicated connection to, say, some other network with which it has high traffic volume, say, for example, a branch campus. Okay. Whereas it may have another one that handles general purpose internet stuff. There may be another one that handles only secure traffic or only video traffic or so on and so forth. So even when we're dealing with the issue of not local and quote unquote send it upstream, as we get to these larger central nodes that tend to handle all entire buildings or entire campuses, it's often the case that we have multiple outgoing destinations. Okay, multiple ways to get to, say, North Carolina. So the forwarding table and the routing decisions can get very complicated, okay, for these larger central nodes. Okay. Now, a concept here we should define, this is pretty straightforward. A default gateway is simply the address of a central node to which anything that we don't specifically know where it goes, we send it to that central node. Okay, so for example, again, looking at my routing table here, 64.106.58.1 is my default gateway. There's the default gateway of the machine that I'm running, recording this video on. Okay, if my computer doesn't know where it goes, where a message goes, that's where it goes by default. Of course, since there really aren't other entries in my routing table, every message goes there by default. Okay. All right, so let's do a quick exercise based on this. Assume that UNM's campus network is organized like the sample campus network a few slides ago, and as I told you earlier, it is. How will a message sent from a desktop computer in the medical school, which is on the North Campus, get to Steve Bird's office computer, which is on the Central Campus? Okay. Well, let's go back for a second to this diagram. Okay. So in essence, what we're saying here, let me undo some of these. Let's say this is the North Campus, this is the hospital, and let's get my pencil here. Say that's the source, okay, from North Campus. And then somewhere out here on Central Campus, okay, is me. Okay. So how does a message get from this computer to this computer? Okay. Well, follow the steps. Okay. From here, a message is going to be forwarded to the LAN central node, the default gateway for this one. That LAN central node is going to look at the address and it's going to say, hey, that's not on my LAN. What do? I hand it upstream. So the first decision is made right there. Now it goes to the Zone Central node for North Campus. The Zone Central node for North Campus knows all of the addresses of all controlled by all of the LAN central nodes in its zone. It's going to look at that address and say, is it in Smith Hall first floor? No. Smith Hall second floor? No. Smith Hall third floor? No. Jones Hall? No. Any other LANs that we don't see on this diagram? No. Okay. And so what's it going to do? Second routing decision is going to be to pass that to the Central Campus zone. Okay. Central Campus node is going to look at that address and say, okay, is that anything on my campus? Answer will be yes. Now the next question is, which zone on my campus? Well, Campus Central node knows which addresses are on which zones. Presumably it will know that my address, whatever it is controlled by this Zone Central node for the Central Campus network zone, and it will pass that message over here. Okay. This node will make the fourth decision, which is which LAN am I attached to? Well, I'm attached to the LAN that controls the east wing of the Anderson School of Management. That'll flow across a connection directly to that LAN, okay? And I'll have another LAN that looks like this one down here, and the final decision, number 5, will be made by the LAN central node that I'm actually attached to, okay? So 1, 2, 3, 4, 5, and then on to the ultimate destination. So that message will pass through 5 different central nodes, basically working up the tree and then back down the tree. Okay. How will a message sent from a desktop computer at New Mexico State University get to Steve Bird's office computer? Okay. Well, we've answered half of that. Okay. Because we know how a message gets from the campus central node to me. It goes through this zone central node and my LAN central node. Okay, but how did the message from NMSU get to the campus central node? Well, presumably their campus is organized somewhat like ours. The sender was on a LAN. It went through his LAN central node. It went through that zone central node. It went to NMSU's campus central node, and then it went out to quote unquote the internet. Okay. Well, somehow from outgoing from NMSU's campus central node to incoming to UNM's campus central node, there was at least one other central node involved. Chances are there were probably 3, 4, 5. Hard to say for sure. It just depends on how many connection points there are between NMSU and UNM and whether those connections are direct or whether they have a lot of indirect ones. In the case of NMSU, I'm actually not sure how they're connected to the internet. Worst case would be where, say, UNM has a connection with Quest, or well, it's not Quest anymore, it's CenturyLink. Got to keep track of the name changes with the phone companies. And NMSU has somebody else, say AT&T. In that case, I wouldn't be surprised if the message goes from Las Cruces to Phoenix to LA to San Francisco to Denver, back down to Albuquerque, and then to UNM. Okay. On the other hand, if say we're both on the CenturyLink network, then maybe there's one hub in a switching center in Las Cruces and another one in Albuquerque, in which case there's 2 intervening hubs, quote unquote, in that internet connection. Okay. But the point is, the upstream from NMSU to go out to the internet looks very much like the example we already did, and once it walks back into UNM's campus central node, the downflow from there to my office is essentially the same. Okay. All right, that concludes our discussion of routing and addressing. Actually, oh no, I'm sorry, we do have one more slide. Okay. Why not use a centralized directory? Okay. Well, first off, what do I mean by a centralized directory? Okay, let's back up a minute and look again at this diagram. And from the point of view of the central nodes, let's ask the question, who knows what? Okay. Well, as we've already discussed, this LAN central node here knows 13 addresses. Okay. It knows the 12 directly connected nodes and this upstream zone central node. Judging by this diagram, this zone central node knows four addresses, the 4 connected LAN central nodes and the campus central node. Looking just at this diagram for the campus central node, it knows quote-unquote 4 addresses, but they're really groups of addresses. Knows the group of addresses controlled by the North Campus Zone Network, the group of addresses in the Central Campus, the group of addresses in the South Campus, and by default other addresses are whatever the upstream central node is, or maybe there's multiple upstream central nodes if there's multiple connection points to the internet. Okay, so even the campus central node in this case, I mean, let's take UNM, and let's just, let's take the North Campus, the Central Campus, and the South Campus. Let's just pull a number out of the air. Let's say it's 25,000. Okay, so in theory, the campus central node has a list of 25,000 addresses. In reality, it's probably smaller than that because it's got groups of addresses bunched into one entry. But thinking of it as a directory, like a telephone directory, there's 25,000 entries in it. Well, 25,000 plus 1, because the 1 being the upstream. Now, let's think about the internet as a whole. How big is the internet as a whole? Well, I haven't seen any recent guesstimates as to how many connected nodes there are to the internet, but let's just pick a number out of thin air. Let's say it's 1 billion. Okay. Well, clearly, my campus central node has a pretty small fraction, 25,000 plus 1, of the total number of addresses known to the internet. Okay. So now let's come back to this question of a centralized directory. If there was a centralized directory of all the nodes connected to the internet, how big would it be? Well, if we assume 1 billion, as we just did before, that's 1 billion lines, 1 billion entries, 1 billion index cards, 1 billion whatevers, whatever the equivalent is inside some database or giant text file. Okay? So that's how big the directory is. Think of 1 billion lines in a file. Okay, 1 billion lines. If each of those lines was just a byte, that would be a gigabyte. If each of those lines was, say, 1,000 bytes, that would be a terabyte. Okay, if each of those lines was, say, a megabyte in size, well, then that would be, is that an exabyte or yeah, it's an exabyte. Gets pretty big in a hurry. Okay, so you'd clearly need a lot of storage to hold that. Although, given the size of disk drives today, we can certainly think of putting that entire directory on one disk drive, or at least on a set of disk drives attached to one machine. More importantly, how rapidly does the content of that directory change? So for example, let's say you're carrying around an iPad. Okay. Well, you might think of that iPad as having one entry in the mythical centralized directory of internet nodes, but the reality, and maybe it does, but the reality is the actual address associated with that is going to change. It's going to change every time you move. So as I, go off campus and go home, now the connection point is no longer the wireless network on campus, it's the wireless network in my home. If I then head out to the nearest Starbucks, well, now it's the connection point at my nearest Starbucks. And of course, if I do all that in the space of 45 minutes, one entry has changed 3 times in the space of 45 minutes. Now you might say, well, not everything's mobile. There's lots of fixed stations. Yeah, but even those can change addresses, okay, for various reasons that we'll discuss. So the bottom line is, this is a huge directory that changes a lot, okay? Now, how big of a computer system do you need to store 1 billion directory entries, okay, handle updates to those on a continuous basis, and answer lookup queries, okay? Answer is probably bigger than any single machine you can buy, okay? Oh, and by the way, that particular server that's going to store that directory, handle update to it, and answer queries to it, had better have a pretty fat connection to the internet, because there's going to be an awful lot of traffic coming through it. Okay, and a final one that we don't have listed on here: what if that poor computer goes down? Okay. Well, if there's one giant directory server for the whole internet and the directory server goes down, how can anybody look up anybody else? Answer: they can't. It's a single point of failure. Okay. So, downsizing from the internet to a campus, let's answer those same questions. UNM, for example. Tens or hundreds of thousands of entries, very rapid content change, wired nodes added, deleted, moved, laptops entering, leaving, moving from one part of campus to another. Okay. A single directory server in that environment would probably be a mainframe, or at least a cluster of mid-ranges. Its network connections would be clogged with lots of directory-related message, and as we said before, it would be a single point of failure in the network. Okay. We don't really tolerate single points of failure, okay, or clogged congestion points. Okay. So as a realistic sense, there's only one answer to this, to dealing with this directory issue, and that is distribution. Okay. If I think of a master directory containing the addresses of all computers on a campus, in essence, that directory doesn't exist as a single piece or as a single data store. It's been broken up into a bunch of data stores which are distributed out across these various LAN central nodes. Okay. Each of these LAN central nodes has an overlapping piece of that directory. Okay, and as a result, failure of any one of these central nodes, while it may knock out a whole zone or a whole LAN, is not going to knock out the entire system unless we're talking about this campus central node. Okay, so the bottom line is, in the modern world of networks, centralized directories just don't work. Okay, there has to be some form of distributed directory with a lot of redundancy to A, just feasibly handle the amount of traffic we're talking about, and B, provide enough fault tolerance so that if one directory server is down, another one can be utilized. Okay. Now, that said, as soon as we do distribute the directory, that creates a whole new set of problems which come under the basic headings of updating and synchronization. If I've got multiple copies of something and that something changes, then I've got to update it in multiple places. I've got to ensure that each redundant data store is synchronized. Okay, that's not a simple problem, but believe it or not, it's a simpler problem than dealing with single point of failure in a centralized directory. Okay, that concludes this portion of, or this discussion on addressing and routing and directories within complex networks.